Here is our discussion of Maxwell's equations. You notice that I'm sitting on the right side here behind the units, and Sam has volunteered to do the hard part.
Wait.
Are you?
Yes, of course.
Here's a pen if you need it.
Okay. So we have the four Maxwell's equations written on the board for you. And under the condition that these are for uniform materials, constant properties in space and time. So let's start with the first equation. This is part of Gauss's law. Del dot E field is the charge density divided by the vacuum permittivity.
Yeah, so rho all refers to two kinds of charges here. When it's all, it's all. So we have two kinds of charges when you consider charges. What are they?
I mean, you have whatever free charges already inside the material.
Any others?
Actually, that's all I can think about. What else?
So bound charges, the opposite of free charges, like when you have little capacitors in the material.
Oh, right.
So all charges.
Yeah, neat. And do you want to talk about the units for these?
Sure. So the units for the charge density, rho, is coulombs over meter cubed. And epsilon naught, which is the vacuum permittivity, is farads per meter. Vacuum has farads per meter. I thought vacuum didn't have anything. So that's kind of weird, don't you think?
No, I think we've gone through that before. Maybe.
Really? Okay. I have to think about it. Lots of physicists had trouble with that one. Okay, let's continue.
Okay, well, for the second equation, I think this is also from Gauss's law.
Yeah.
And we have del dot the B field, the magnetic flux density, equals 0. And we'll go through the physical interpretation of that later. And do you want to go through the units?
Yeah, sure. The units of B are Webers per meter squared. So notice the difference here. This is Webers per meter squared, meters cubed per meter. I wonder if there are any other quantities that are something per meter squared.
I bet we can dig into that later. And third, we have Amperes Law.
Oops.
Is this not an Ampere? Oh, no, Faraday.
That's okay.
Third, we have Faraday's law. Del cross E field is the permeability times dH dt, the change in magnetic field over time.
And now look at the units. The units are electric field, volts per meter. I got the easy one. H, magnetic field intensity, amps per meter, and mu, the magnetic permeability, is henries per meter. Farads per meter, henries per meter.
I see some parallels going on.
Right, so one more to do.
Okay, and this time the actual, I'll not get this wrong, Amperes law. We have del cross H is a bunch of current densities. We have the source current density, conduction current density, and displacement current density.
And the units are amps per meter squared, and we can see that there are three different current densities: source, like a generator; conduction, like, turns out, Ohm's law, which we've seen before; and something new here, displacement current density. So I think we're pretty well done. Are we?
Actually, wait.
Is there something we're missing with units?
Yeah, so when we look at the current densities, for example,
Yeah.
you have amperes per meter squared, all right? But H has ampere per meter. So how do we make the meter match with the meter squared?
Oh, okay, so let's look at this equation in terms of units. We forgot one thing, the units of this. The units of H is equal to the units of all the currents, J. So as you just said, this is amps per meter squared. This is amps per meter. That means we're missing something.
So the nabla has 1 over meter.
This has to have units of 1 over meters. And that's something you'll not see in any textbooks. Sam, why does the nabla have units 1 over meters?
I guess that's because it's a change in position. And
Yeah, it's a derivative. So elements of that are things like this. So we're dividing by distance. So the operation, this is an operation, is 1 over distance. And so now everything balances. This is a really, really important result. Without it, we won't get the right units.
agreed.
Great. So let's go on. We're going to start to look at what the interpretation of these equations are, both the physical and mathematical.
Sounds great.